Good afternoon. I'm welcome to the Swansea University Climate Change Emergency. My name is Sian Whittaker and I work for the emissions team in Science and Engineering. I'm delighted to introduce to you Dave Penny and Tristan Watson, who can give you the talk tonight on materials engineering and solving the world's energy crisis. I will be on hand after the talk this afternoon to answer any admissions questions that you have, but I will hand over to Dave and Tristan, who will give you the talk and any questions you have later. Feel free to put them in the Q&A or the chat function. Okay.
Thanks, Sian. Hopefully you could all see my slides now. Let's go straight to the end one. Here are my slides. As Sian said, my name's Dave Penny. I'm a professor of materials at Swansea University. My details are there on screen, so if you want to get hold of me afterwards, if you have any questions, then please feel free. Very happy to chat about any of the subjects today or anything to do with materials. So first of all, I mean, many of you might not have heard of what a material scientist is. In fact, has anyone actually have a clue what material science engineer or scientist does? Anyone? I don't know if you can actually put things in the chat, but if you've got an idea, stick them in the chat. It'd be interesting to hear what you think. Also, if you've ever come across one, because we're quite rare. There's not many of us around because it's like a hidden subject. You know, everyone's heard of physics or mechanical engineering or aerospace engineering, but materials engineering is one of those things that people haven't really heard of, which is good in a way, because it means the class sizes in materials are quite small, and you're always going to be sought after when it comes to getting jobs. So I'll tell you a bit about what materials is. So it's the study of structure of something and how you can manipulate that or control that to alter the properties at the end. So what I mean by structure, well, you can talk about the atomic structure, right down at a very, very small scale, or the microscopic structure, sort of the tens of microns type scale, or then the component side. So you think about an engine or a solar cell or things like that. And then what you can do with altering the properties of the structure of those materials, so altering the microstructure or the atomic structure or macrostructure, you can then influence the properties of that material. So whether that be how strong it is, making it stronger, making it more flexible, or whether it's more conductive or less conductive if you want it to be an insulator, or you can make it look nicer, look shinier. All those sort of things you can do by influencing the material structure. You can then make the properties you want. So it's quite an interesting and varied role, because you can cover almost everything. So you have the materials professional in the middle. So it's everything to do with everything. It's materials, which is why it's quite a hidden subject, because it's hard to nail down into what it is. Because people work in all sorts of sectors who do materials engineering. You'll find civil engineers and civil engineering sector is desperate for materials scientists. You know, if you think about the Severn Bridge coming into Wales, those big structures, they've been there a few years now, and there's some corrosion occurring on the big support members. So material scientists are helping to try and prevent that. We're pumping nitrogen up through the support members to stop it from corroding, and doing all sorts of interesting stuff with the materials that is used so they're more durable and stronger. Think about mechanical engineering, that's fairly obvious. You know, when you talk about gears and anything to do with moving parts, the biggest cause of failure in mechanical component is a thing called fatigue. Fatigue is when you bend a material backwards and forwards. So if you think about a paperclip, you grab a paperclip, you bend it once, yeah, fine. Bend it twice, yeah, okay. 3 times, still okay. Maybe 4 or 5 times, it's going to snap. So the force you're using is the same. You're not increasing the force, you're just doing it more and more times. So this repetitive cyclical type stress is called fatigue. Happens a lot in mechanical engineering, and it's responsible for about 90% of the failure of components out there. So if you think about cycling a bike, your pedal shears off, it's down to a thing called fatigue. Aerospace, you know, think about jet engines now. They're running at really high temperatures. It's the higher the temperature, the more efficient the burn, the less fuel you need, the more efficient they are in terms of carbon emissions. But they're operating at 1400 degrees C. You know, that's up around the melting point of nickel. It's very, very high temperature. So materials engineers are in huge demand there to try and engineer those engineer those materials so that they can survive. Energy, I'm not going to say too much about because Tristan's going to do a brilliant lecture talk about energy in a second. Chemical engineering is about movement of material. Again, lots of interaction with materials there. And medical, if you're unlucky enough to need a fake hip, then that medical will sort you out there. But also around imaging in medical. And when we get to imaging, here's some pictures of some different materials at different scales. Here we have some steel, and using our microscopy techniques, we can see where the cracks are formed and also plot the stress area. So we can see where cracks might form, and you can see at these 3 points here where the grains are joining, there's extra high stress. So you might form a crack around here, or you might form a crack here. Here's an image in the center of a nickel superalloy, which is we've added these precipitates or grown these precipitates with these square things here. And that what they do is when the materials are high temperature under stress, so if you think about a jet engine, high temperature, 1,000 odd degrees, with rotating so fast, it's the equivalent of having 2 double-decker buses hanging off the end of the turbine blades. So it's a hell of a lot of stress. These precipitates help to keep the material in one piece. Here we have a ladybird's face. So one of our colleagues in materials, he's doing bio-inspired engineering. So looking at how nature has solved certain problems. If you take a cuttlefish, they can make themselves buoyant or less buoyant by filling these highly complex networks inside their bodies. So we can scan those and then replicate them. So a lot of work going on around there. On the bottom right here, these are individual crystal atoms, crystals. In I think it's gold on this one, so you can see the individual layer. So this is a nanometer scale, nanometers, you know. So this sort of microscope we used here can image things which are the same size as your fingernail would grow in a millisecond. So that's very, very small features indeed. On the top here we have a metallic coating which has got these precipitates in which hold corrosion at bay. So lots of interesting microstructures of materials and how you can change them to give you better performance. Tomography, here we have using our imaging techniques to look at various things. On the left here, we've got an Egyptian mummified cat. So obviously you don't want to start unwrapping them because you'll destroy the artifact. So by using X-ray tomography, you can visualize what's inside the mummy without damaging it. So it's essentially an X-ray in three dimensions. So you rotate the sample inside an X-ray, and then you can see what's behind. And the bottom we have some sort of grub or beetle, a grub or maggot type thing. Don't ask me why he scanned that. Obviously, Richard, the guy who runs that lab, is quite interested in these sort of things. And on the top right, we have some coke. Not the coke which you drink, obviously. The coke you use in a blast furnace for making steel, and we can look at the porosity of it. And if you can tune the porosity, you can get more efficient steel making process. Some testing of material now. On the left-hand side, we've got some material being hit with a hammer, and you're looking at it straight on. So the photographer or the filmmaker, lucky not to get a hammer in the face there. But what you've got there's 2 different types of material: a ductile steel, which doesn't quite break, and a brittle ceramic, which does break. And what you can do with these things is you can tune the properties of the material and then see how much energy is absorbed by hitting it with a hammer. Seems very, very no, not very subtle, but it does a job. On the right-hand side, we've got a tensile specimen where you're pulling a piece of material apart and measuring the stress required and the change in length. That's important for things like, but if you want to engineer steels, for example, steel is a wonderful material. If you think about a can of Coke, again, the thickness of that is about the same thickness as a £5 note. And that's one type of steel. And if you think about that, you can just crush it up really easily with your hand. You get another type of steel which you use in your car, which if you don't want that to crush up if you get hit by another car. In fact, my wife, she was in a car on the motorway, and the traffic slowed down in front, and the car behind obviously didn't see and rammed right into the back of her. And when she got out, making sure everything was okay, the car had completely crumpled, and she thought, "Oh, that was a bit of luck. If it's crumpled like that, it's absorbed all the energy, and I'm okay." But it wasn't luck. It's how materials engineers have designed the material to crumple like that to absorb the energy. That was before, obviously, she got to know about materials. but then you realize around life into a lot to do. It's material testing for something else. Corrosion, who think probably none of you, dollars a year. It's every weekend one kind of steel. It's a hugely expensive thing. And if we look here, we have a coating which has got magnesium and zinc in, and we're watching it corrode over time. So this black area here, which looks very sinister as it travels through the steel here. So these dendrites are about 20 microns across, and they're dendrites because they look like trees, which is the Greek for tree. And what you can see is the dark phase, this dark area, the corrosion is traveling in between these bright dendrites and causing some corrosion to attack that one particular phase. So what we can do is alter those dendrites, so make them bigger, make them smaller, and try and prevent that corrosion from progressing. Bottom here, we have some thermo-electric materials. Now, these are really interesting materials because when you apply, when you have a temperature gradient, so if you have these materials strapped to a hot metal surface or a hot surface in a factory, the hot side on one side, and then there's a cool side on the other out in the environment or with some sort of heat sink, it will generate a voltage. So what you can see in this video is that as it gets hot on one side, you're generating a voltage. So this is really good for scavenging energy. In manufacturing, materials obviously heavily involved with manufacturing. You think about, rolling, coating, extrusion, forging, all these things have been used for a few years now, and materials heavily involved with that. But if you think then about some of the new techniques coming through with additive layer manufacturing, which is like 3D printing, you've probably seen that with plastics, but now with metals as well. And you can see these quite complex metal structures. And we're looking at how we can make them better, make them more durable, and also perform better in service. So why is materials important? Well, obviously energy, which Tristan's going to talk about. All the big challenges we're facing at the moment around climate change and energy and health and resources are going to need material science and engineers. One of our students was looking at the waste from a local factory which had thermocouples to measure the molten metal temperature, and it had platinum in very small amounts of platinum, and he managed to take that platinum and turn it into an ingredient for solar cells, which Tristan then used to make some solar cells, where previously he was buying those ingredients for hundreds and hundreds of pounds, whereas Reese, the student, managed to get that material out and use it for a few tens of pounds. So a quick example of this, which I think won't go too much, but this is one of the projects that's going on at Swansea at the moment with a guy called Dr. John Alvins. He's looking at taking vermiculite, which is basically, like you see in the middle, like cat litter. It's not dissimilar at all, very light sort of ceramic material, full of pores, and then impregnating that with a salt, calcium chloride. And you can see that on the bottom here. So you get this salt impregnated into this matrix, and you can see an X-ray image of it there. And then what happens is that salt, when it gets wet, gives out heat. So what you could do then is you can impregnate this vermiculite with this salt, and when it's dry, or you can dry it out using waste heat. So you can take this wet vermiculite, take it to a factory which is kicking out loads of waste heat, dry it out, and that's then storing that heat. So when you want to release the heat, you blow cold, moist air through it. The moisture will activate the salt in matrix and will give out heat. So if you think about it, you could store heat then indefinitely. So you just take a big box of this vermiculite, which has been dried out with the hot, and then you use that then when you're ready by putting cold, moist air in, and you get the high temperature out. And you're thinking about, you could take the waste heat, say from like Tata steel, and you can then put it on the back of a van in something the size of a fridge, and then you can use it to warm your home. That's the plan for some of the work we're doing at Swansea. So if you did decide to do a materials degree, you cover modules which cover all sorts of structure, properties, where materials come from, how they're used, how they're recycled. We look at packaging and how you can reduce waste from packaging. We're looking at failure mechanisms. We talked about fatigue at the beginning, also corrosion, those sorts of things. And also their manufacturing techniques like ALM or more traditional ones. Obviously, computational stuff is very important, and we teach people how to use computational programs for predicting microstructures or for modeling fluid flow, that sort of thing. And throughout, lots of lab work. So you get to use these skills in the lab, and we bring in company partners who support it through proper case studies of real life issues. And lots of group work and lots of community feel, so everyone's feels part of a bigger thing and has plenty of help on hand whenever they need it. Careers, almost everything, across the different sectors. We've got people who've done a materials degree and now working across all these different sectors. And our employability is quite good. So 97% of materials graduates go on to earn £28,000 within 6 months of graduating, which is above the average. So yeah, so materials, good interdisciplinary subjects, lots of career options. You can go into almost anything, lots of world-class research. But now on to Professor Tristan Watson. So I'll hand you over to Tristan. I'll stop sharing.
Right, well, hello everybody. Absolutely delighted to be here. Thank you so much for that, Dave. Every time I hear you speak, I think to myself, how many materials degrees can one person have? Where do I sign up? So absolute triumph of illustrating just how important and potent materials is in everything that we do around us. And I always say to the students in Swansea, if you want to make an impact, if you want an opportunity to spend decades of a career having a genuine impact, whether that's in solving the world's energy crisis, like we're talking about today, supporting climate change, reducing the demand on our planet, using less resources, and you're sitting in a materials engineering degree lecture, then you are in the right place. And I spoke to some students this morning talking about the circular economy and trying to look at how do we mitigate the amount of raw materials that we take out of the ground. And I said, and halfway through the lecture, you could see that the students were itching to think, what can they do? What can they do? To a certain extent, it's be patient, develop your expertise, learn about materials, learn about what's important. And within two or 3 years, they were first years. So within 2 or 3 years, you will really be able to go out and get your first opportunity to make a difference. And it's people doing materials degrees that I think is going to be one of the biggest weapons against climate change that we're going to have. And I was really excited to start their journey. Okay, so let's talk about some interesting things. Can you let me know, Dave, whether I'm sharing my screen okay? If I press play, can you see my slides?
Yep, all good.
All right. Okay, let's go for it. So what I wanted to speak to you today, I think Dave has really nicely covered the foundational principles of materials, and he's talked about a load of different applications. And in reality, if we were given a 5-hour slot, we still wouldn't be able to get to the end of all the various interesting things that the materials engineer can do. So we have to be selective. And in reality, even with 5 hours, we'd still be talking about the really interesting topics. Yeah, we wouldn't even be coming on to the things that are perhaps able to give you a high earning job, but maybe are not particularly interesting. And so in reality, we often talk about materials that are well known to people, like graphene, for example, is a good example. We see a lot of activity in SpaceX and aerospace, the sort of things that go on in your phone, semiconductors and light emitting diodes, and new energy materials, new batteries, new solar cells. And this is just a very small list of a number of things that all have one thing in common, and that they were all developed or conceived or pounced upon to exploit by materials engineers. So when we look at all these fields, we think about graphene, we think about highly conductive materials, understanding the conductivity of those materials, understanding the application. We look at SpaceX and this wonderful work that's going on at the moment in terms of exploring beyond the boundaries of our planet. And we look at the fact that there's only certain materials that can withstand the sorts of conditions that you see as you go in and above the Earth's atmosphere. Recently, we had some project work by some students and that led to a publication, and it was all about understanding what solar cells could withstand the proton radiation hardness of space, for example. And this is, these are sorts of common things going on every day in Swansea University. Similarly, at the bottom left-hand corner, you can see semiconductors there, and we're working really hard to understand the behavior of semiconductors. How do we print semiconductors? How do we get them down and working at very low cost? And every time somebody in the field of semiconductors gets those materials closer and closer together, you get a new iPhone and you get a new chip that goes into the iPhone. And so every time a materials engineer is trying to drive those things closer and closer together, we see massive innovation in processing power within the computing industry. And we're lucky enough that the materials engineering department is linked with the new Centre for Semiconductor Research, which is being opened in Swansea University. On the bottom right-hand corner, we see huge differences in the materials field in energy materials, both in printed solar cells and the development of batteries. And the field is really waiting for people to come and do materials engineering, because there is a long list of challenges that we need to meet. We don't yet have a room temperature superconductor. A room temperature superconductor would completely change the world. It would allow us to have this very, very highly conductive material with no resistance at a temperature that doesn't require a huge energy input. That prize is still on offer. We think about lithium batteries. Not every country has access to a really good supply of lithium. And so if we want to use batteries and develop batteries that have the same capability as a lithium ion battery, we may need to use sodium, for example. And a lot of countries have access to sodium for obvious reasons. And so how do you make a sodium ion battery which is as good as a lithium ion battery? These challenges are still available and still out there to be won. And so, there is a certain excitement that exists around the materials engineering field about who's going to be the first, and these things will carry on over the next decade, and there'll be the next set of really, really cool challenges. And they're all generally linked by what Dave has just spoken about. So it's not just about the development of materials, although that is the job of a materials engineer. It's also about understanding them. So you can understand how the structure exists, the properties, the performance of that particular material, but then how do you make it? How do you process it? And when you've made it, is it going to do what you want it to do? So I'll give you a simple example there of trying to make a printed solar cell, for example. You need to put the solar cell down in a certain way. You need to make sure that it works as well under the sun. And then you need to measure it afterwards to understand whether you've sort of completed the whole story. So materials engineering really plays a role in a vast array of some of the things that you might consider to be some of the world's most exciting technology challenges. And we work with the interface with chemists and physicists and mechanical engineers and chemical engineers to make this come to a reality. But if you want the person that really understands the materials itself and understands the way they behave and understands the demands of that particular material, then it's the materials engineer. Now, people get very excited about the things that are on the screen at the moment. I actually get very excited about something else. I think this is the greatest opportunity for us to solve the world's energy crisis. This is a building, and there is about 40 million square meters of this, 4 billion square meters, I should say, of this material in the UK alone, doing something incredibly well, and that is keeping the wind and the rain out. And what else is it doing? It's not very much. So we have 4 billion square meters of real estate, effectively, that faces the sun most of the time. So if we could, say, use our materials engineering skills to develop something that might, say, turn that energy into something useful from the sun, might we be able to make a difference? Is there something that we need to do differently? This is the British electricity live map from an excellent website called MyGrid, where you can access the data for the behavior of the usage of electricity in the UK at any time of the day. And I think this was last week during the afternoon. So there was not a lot of wind like there may be now. There was quite a lot of gas on the grid. So 50% of the electricity produced was gas. And there's a little bit of renewables, some solar, some hydro. What you'll notice from this, though, is that there's actually not a huge amount of renewable technologies. And in fact, most of it is still fossil fuel generated. So gas and coal and biomass are all the fossil fuels that we see. And so clearly the UK energy mix is dominated by a non-renewable energy source. And that is something that we can do something about by taking this wonderful invention and doing more with it. So what this talk is about thematically is how do we take a building and turn it into a power station so that we don't use so much from the grid. That's only half of the story though, because if we look at the energy challenge within the UK at the moment, the red line there you'll see is the electricity that I've spoken about. And that's something that we can make a big dent in if we use less electricity. Actually, the blue line is possibly more problematic. The blue line is the gas usage. That is vastly more. And that gas goes often into domestic buildings like the building that I've just shown you there in order to heat up the building. So imagine a scenario where for both of these problems, both the fossil fuel produced electricity and the gas that often has to be imported, all fossil fuels, again, non-renewable energy sources, how can we use that building to generate, store, and release energy? And that is one of the major themes that we investigate in one of the research projects in Swansea Materials. So Swansea University Materials is the home of Specific, which is an innovation and knowledge centre, which is dedicated to trying to develop the next generation of renewable technologies that can be fit into a building, to do something a bit more than keeping the wind and the rain out. Ultimately, we can, if we want to, rely on fossil fuels, but our time is numbered. And we certainly won't be hitting 1.5 degrees of temperature increase if we keep looking down for our energy. What we probably want to do is look up. And in the sky, there is thankfully a gigantic nuclear reactor, which is not about to fail anytime soon and produces at least enough human energy falling on the Earth every single day that we can use in the next 27 years. So my question to the future materials engineers is, how do we do more with this vast resource? So instead of digging it from underneath our feet, how do we capture it from above our heads? And so this is one of the biggest challenges. So take the building as an example. What can we do? Well, firstly, one of the perhaps more simple ways we can do it is we can put solar cells on the roof. Now, a solar cell, in this case is a photovoltaic, is something that takes in the sun's electricity, sun's energy, and turns it into electricity. It's not about heating water, although those are good things. It's about creating electricity. In the top left-hand corner, you'll see an image of a roof on the Swansea University campus, which actually has the solar cells already integrated into the fabric of the roof. So instead of having to persuade somebody after they've made the building to put solar panels on, the solar roof itself has the solar panels. Now, certain solar cells actually produce heat when they're in operation, and that heat is often wasted. So how about we build another technology into the building, that's the top right, that takes that energy that's produced both in electricity and in heat. And this is a product by a partner of Swansea University, Naked Energy, to produce solar thermal. So now we have a product that goes onto this building that produces electricity and it produces heat. Now, sometimes, bottom right-hand picture, as Dave has mentioned, you can take the heat of the sun and turn it directly into electricity. Again, a technology that exists called thermo-electrics. So the top left is sun to electricity, the top right is sun to electricity and sun to heat, and the bottom right is heat to electricity. All of these require a different materials engineering approach to design them, to develop them, to manufacture them, and to put them together in a building. In the bottom left-hand corner is a very simple technology that we also use in our buildings, which is effectively steel with holes. We make that steel very hot by shining the sun on it or by putting it in the sun's rays, and we draw some warm heat from the boundary layer around those holes into a building. And you can get 5 to 10 degrees of uplift, which is a significant amount on a cold day. And these are, again, materials challenges. The bottom left in this image, electrochemical storage. This is the term for batteries. And this is something that in the world of science and engineering, we are going to be seeing a lot of in the next 50 years. When we produce electricity from the grid, we typically have to use it all at once. We have to demand manage. In other words, we produce electricity and then we use it because we knew we needed it. In reality, there's wind often when we don't need it, and there's light often when we don't need it, and we can import electricity often when it's cheaper. So if we can store that electricity through renewable technology development in a battery, that allows us to really manage the way in which you use electricity. And one of the key areas of our research in Swansea in the materials department is how do we develop the next generation of batteries? This is an absolutely wonderful challenge because it requires us to store as much of the electricity as we can without wasting it in a system that doesn't cost too much to build. Now we can see the absolute potency of batteries just by how Tesla have come on and how electric cars have come on, and there's no denying that those technologies are really at the forefront of the global revolution in converting transport to green methods. And it's part of the story is the development of new batteries. As I said, in some countries, there's no access to lithium. So it's not necessarily a direct production of lithium batteries. We need to develop alternative batteries that don't use lithium, that may use other materials, as I said, like sodium. On the right, you can see that Dave also touched on thermochemical storage. Now, what if you had a building system, something that was built into the system that was able to take in heat during the summer and release it during the winter? In fact, I'll ask the question, why don't we do that already? There's plenty of heat in the summer. Why are we cold in the winter? Why don't we just keep it in the summer and then bring it back out in the winter? And the reason for that is because there was a technological challenge as to how we do it, which stood in the way of that. In the last few years, some excellent materials engineers in the world scientific population have started to understand what the best way to do that is. Of course, you can heat up water and you can keep that warm for quite some time if you insulate it properly, but not generally within a few months or 3 or 4 months, which is what we really need. In the UK, we need summer to winter. But as Dave said, you could use salts, you could use new materials that are being developed at the moment to take the heat from the summer, lock it away, put it away for somewhere, enjoy your summer holidays, and then as the weather starts to change, as the leaves start to fall from the trees, you can press a button and release that well-kept energy that you put away. That is a technology reality, but it's not perfect. So it needs people to come along, study materials, and take it to the next level. So all these materials are exciting, but they don't work very well independently, or they work very well independently, but they need to come together in order to create the whole. And so what we've done in Swansea then is to achieve that by making actual buildings. So we made a classroom, which if you came to materials, we would teach you about functional coatings and functional materials in a classroom that was powered by functional materials. And during the course, I'd be able to point out these various technical innovations to you that are keeping you warm or keeping you well lit or keeping you sane, dare I say. So this is in the bottom left. This is a building that is completely off-grid and is powered throughout the year by renewable electricity that is integrated into the building using developments that have come through from students that were once upon a time studying materials engineering in Swansea that have helped to integrate these things together. We need to measure them and we need to understand how they work together. So when you make a technology, you need to make sure that it understands and cooperates with the other technologies. So you don't want both your systems producing heat and too much heat. If you've got 2 or 3 technologies that can produce heat, one of them can also produce electricity, you might balance the system to produce more electricity than you do heat, or you might store that heat in a thermochemical process. So how do you balance all of these various input flows of renewable goodness to make sure that you've got the output flow of never having to borrow or take any electricity from the grid structure, off-grid buildings? And that was so successful that we thought we'd have a crack at making another building. So in the right is our active classroom, and then the left is our active office. Now the active office is a real revolution in that you've got flexible PV, you've got the next generation of some of the technology. So we learned a lot when we did the active classroom on the right, and we built in some of those lessons into the active office that we've now manufactured on the top left in the left of this image. And so we are able to really gauge what works and what doesn't work. Now, say you're one of our students in materials, and Dave said you'll get a chance to do lots of prac work and you might have a really good idea. And we like students to have good ideas, and we very, very actively support them to become the next big idea. So if you've got a new idea in the next generation of renewable technology, how do you take it to the next level? How do you prove that it works? Well, in Swansea, we have laboratories to show that you can make it work at the small scale, but we're one of the few universities in the world that also has its own factory. So not only can we take good ideas and show that they work in the lab, but we can take good ideas and we can show that they work in the factory as well. And we need that to demonstrate the feasibility of something. So if somebody has a good idea and they're able to make a small quantity of material to show that it might be the next big thing in solar technologies, then we can show using our manufacturing techniques whether it is scalable to a much larger scale, and ultimately to a scale at which we can put onto a building. And some of those things are happening at the moment, where we're trying to make building scale solar cells, for example, that we've printed ourselves in the team at Swansea University. So as I said, solar technology is our friend in how we develop these things, but it's just worth reflecting a little bit on the technology evolution of solar research and solar technology research, because we are not the giants. We are building on the shoulder of giants. Lots of work has gone before, and we're here as engineers to take it to the next level. When it comes to solar, we can look back as far as 1200 BC to the Puebloan people who built their houses in a very clever way to absorb the sun's rays during the daytime, that then kept their buildings warm in the nighttime. This was a really important method for them to be able to exist in certain environments where they might get cold. If we think about how do we apply solar cells, we can apply them onto boats, and Max Schick did this in 1959. And it was until 2010 that we did these grand round-the-world voyages using the planet solar, using completely powered by solar cells. Now, you might think about solar-powered cars as something for the future. When I think about it, I have to go back to the Baker electric car in 1912, which, as I understand it, had a range of about 100 miles. This was highly innovative people trying to do things where even the technology wasn't quite there yet. Thankfully, during the intervening time, we had a World Solar Challenge of car that was able to go around the world in 2017. Even in airplanes in 1981, they were powered in this way by solar cells. If we skip forward to 2015, we've got the Solar Impulse, which was able to go around the world using solar power. Now, when I talk to my team about how we can get the next generation of solar cells onto buildings, I actually have to go quite a long way back to remember the pioneer of building integrated photovoltaics. Because in 1883, it was Charles Fritz who created the world's first solar array. And there you have it, the first mounted solar cell on a building in 1883. I would say that we've come quite a long way in that time, because at 2020 and 22, we're now at fully active buildings, even in the UK climate, that doesn't need to take any additional electricity. This man is an important innovator in functional and smart materials. This is Thomas Edison. And he said in 1931, I'd put my money on solar energy. I hope we don't have to wait till oil and coal run out before we tackle that. One of the joys of teaching materials in Swansea is that I get to stand in front of some incredibly intelligent and enthusiastic young people and ask them this question and say, do you think we're at this point? And invariably the answer is, no, we're not there yet, but we've really got to get on soon. And so it's great to see their enthusiasm, that they're itching to come on. And Swansea University can give you the tools that will allow you to make a difference in the short space of time we've got left to revolutionize the energy industry. So this is where we want to get to, and some of the work that we do in Swansea is involved in printed PV. And just to briefly touch on the sort of research that we do, which is quite interesting, we do lots, and in third year of your course, you'll have an opportunity to work in the laboratories and do research, and you'll have lots of contact with it in the preceding years as well. We do lots of different solar cell developments and design. So this is something that we've been doing for a while. We print them in lots of different ways. So instead of making a solar cell with great expense and high purity, in China, for example, which is where 90% of solar cells are typically manufactured, in Asia, we can actually make them and develop a process for printing them here in the UK. And that's something we're really enthusiastically developing in now. How about we create a solar industry in the UK? So we do it via processes called roll to roll. So this is my team printing solar cells. A few weeks ago, it was featured in the BBC Click Online program with Lara Lewington. and they came and did a story all about how we've managed to print some solar cells onto flexible surfaces that you can bend. You can wrap them around buildings. We do them on sheet-to-sheet methods, and we develop all the processes. So Dave mentioned what is materials about, not just characterization and understanding of the materials, but also the way which we process them. So we've developed this method for making a solar cell, and you can see this is one of our solar cells being manufactured in rapid time using processes entirely developed by the research team in Swansea. This is an actual module of a solar cell that's never been made in the UK. The UK doesn't have a solar manufacturing industry at the moment. So when we make solar cells in Swansea, they are really the first of their type to be made in the UK. And so we're very happy to see that we're also making the first ever solar modules made in the UK. So that's my final slide. I just wanted to sum up by saying that what you can see on the screen there are materials engineers, and what you've seen throughout are materials engineering challenges being solved by people who've studied materials, and some of them from Swansea University. So thanks very much for listening.
Thanks, Tris. So I've been trying to answer some of the questions in the chat as we go along, but if anyone's got anything else they want to ask, please either stick them in the chat, or as Sean's put in the chat as well, you can email her s.e.whittaker@swansea.ac.uk, or there's me, d.penny@Swansea, and Tristan's t.m.watson@swansea.ac.uk.
Yeah, that's me.
But yeah. So materials in Swansea, there's a few different subjects. There's mechanical, civil, aerospace, materials. But I think 70% of the research funding in the College of Engineering is with materials. All of the funding in aerospace, pretty much, that's from people like Rolls-Royce and Airbus, is in the materials department. So it's an area where there's lots of activity and lots of funding to do some interesting research. Someone's got their hand raised, Sean. Can you say, you unmute and ask a question? Fire away. Just need to unmute.
Yes, sir. Yes, sir. Thank you, sir. I'm grateful to attend this event. However, I ask you several questions to you that actually I have a keen interest on inorganic building insulation from waste industry slab. Most of the people don't use electricity. How, from using this kind of things, how could we regenerate electricity and could provide more electricity to our people?
So your internet connection is not fantastic. It was quite difficult to understand them. But if I pick out some things, were you asking about waste materials like slag and also waste energy from processes like that? Yeah.
Yes, sir. Yes, sir.
Well, I suppose, the waste energy, as I think I put in the chat, the problem with companies are quite good at dealing with high temperature waste energy. So if they're very good at taking that high temperature waste energy and putting it back in the process. Where it gets more difficult is at the lower temperatures, below 100 degrees, where you can't boil water to make power, or it's not so useful. So that's where the salt-in matrix work, which I described and Tristan described, is quite promising there, because you can store that forever. You can take that waste heat, store it by drying out this vermiculite and this salt-in matrix, and then use it when you need it. The other interesting areas for that is the thermo-electrics. Some of these printed thermo-electrics are being applied in companies like Tata Steel around pipes, or they're trying to apply them around things like that. So you can get some voltages, some energy from there. And then, of course, as you rightly point out, the waste materials. So things like slag and dross gets reused already. So if you take dross, which comes from the galvanizing plant, which is zinc oxide, and normally could be landfill, but now they're turning it into makeup and sunscreen, and they're finding more interesting ways of turning that zinc oxide, which is at the moment not very useful, into zinc oxide, which is a semiconductor and used in electronics. So there's lots of research to take these waste materials, and turn it into something useful. And I think it was you as well who put the thing about the electric cars in the chat as well. It's a very good question. All these electric cars use things like cobalt, lithium, all these expensive and hard to find, or at least hard to find and ethically. Cobalt is often mined in areas of the world where they don't have brilliant child labor laws, things like that. So I think Tristan mentioned the battery research at Swansea using sodium instead. So we can either replace that technology with less harmful materials, or we can build in some sort of design for reuse at the end, or take back. And that is a huge area which we teach in undergraduate materials. And there's also lots of research in this, and there's a couple of my colleagues, Matt Davis and Reese Charles, you can look up, and they're doing lots of brilliant research on this sort of thing and influencing policy.
This morning, in fact, I gave a lecture to first-year materials on the use of materials within the circular economy. So as Dave mentioned there, we typically see materials as a linear process. We mine it, we process it, we manufacture it, and we consume it. Whereas in reality, if we think of all those things in a line, that's a wrong look at it. What we need to do is we need to really circulate it back. So when Dave talks about reuse, it can be recycling, it can be remanufacturing. How do we get the best out of our material? If we think about aluminium as an example, aluminium, we can generally recycle aluminium with about 1 to 2% of the electricity use, of the energy use, the second time round. Yeah, so we can actually take aluminium and reprocess it in secondary aluminium with much, much less energy than goes into it in the first time. And yet, a lot of the time, we bury it under the ground instead. So there's lots of really cool challenges, not just in batteries. So, okay, any other questions? I think we can continue to take some questions if anybody has them in the chat. If they'd like to verbally ask the questions, they can, but we can certainly field as many questions as you want, and we can chat. We can unmute you if you'd like.
That's very kind of you to say. Yeah, and if you come to work at Swansea, if you've been offered your degree here, then you can definitely pick to do projects with either of us, or even work with both of us. Who knows?
Yes, yes, definitely.
Yeah. So your internet connection is a bit wobbly.
So Dorian, Juan,
Yes,
Mervyn,
sir.
Richard, let us know if you've got any questions.
If not, I think we can bring this to a close. Sean, is that okay?
Well, sir, one more.
Okay,
Well,
sorry,
sir,
go ahead.
one more question. I have to ask you about. Well, about corrosion. Actually, I have seen in India there's I mean, which is called Qutub Minar. Since duration, it hasn't got a corrosion. However, nowadays corrosions become more problem. So, is there any other way rather than galvanizing or
I think his
I
internet's
don't know if
dropped out.
his internet's dropped out there. Yes, yeah. Did you answer the question about nuclear fusion there? Did I miss that one?
No, that's just come up. I
Right.
think nuclear fusion is an interesting concept, and certainly, without a doubt, it has a role to play. There's a role to play in trying to find out the legitimacy of nuclear fusion. So when we look at the net power that goes in versus the power that comes out, obviously we always have to have a significant amount in that balances the investment that goes into it. So that number has to increase a lot in terms of the energy in versus the energy out. So the requirement to contain the particular novel materials that allow nuclear fusion is incredibly challenging at the moment. And so there is an element where at some stage there might be a technological possibility around nuclear fusion. It might be just under the realms of expense in order to demonstrate its feasibility. Certainly, there are lots of research going into nuclear fusion, and I'm not an anti the idea, but we've got to see it progress to the next stage beyond small scale reactors, I think.
There's an additional question there on thermo-electrics as well.
So thermoelectrics, the principle of thermoelectrics is again about semiconductors and the heat differential between two different materials. In reality, you want there to be the temperature difference that then produces the electricity. So with a thermoelectric, you want there to be as much heat difference between two types of material. So there's no loss of heat necessarily. It may be that the heat is not used appropriately by the material, but in reality, it's the difference in temperature between two materials that drives the production of electricity. So you don't lose heat necessarily in a thermoelectric, but you may not use it effectively. The other thing is that the temperature difference that you can achieve in order to start generating electricity can be quite high before you can actually get some change in the electricity production. So what you would do with combining, and that's a very good question, Juan, actually, because in reality, combining technologies is often the key. So if you want warmth and you want electricity and you also want light and you also want heat to come, there is going to be a combination of technologies that allows you to do that without wasting anything. A good example of not wasting electricity is in solar cells, where we mount solar cells one on top of each other. So sometimes a lot of the light passes through a solar cell and just produces heat, for example. But if you line them up one on top of each other, you can capture as much of the broad spectrum light as possible. So in answer to your question about thermoelectrics, you would combine it probably with another technology.
Perhaps, but if you're asking, like, would you put a thermoelectric on a radiator in your house? No, you wouldn't, because you want that heat to be, that heat is already being used. It's being efficiently used to heat your house. Where you might put it though is on the pipes in the boiler or outside, if there's only waste heat, or in a factory where there's already lots of heat. That's where you would get the most use out of these materials.
Yeah. Yeah, and industrial waste heat is a massive thing, and something that Swansea University has got a real research activity in the moment. So not wasting anything. We do waste a lot in manufacture, and we use fossil fuels to do a lot of this manufacture. So if we're going to use something as precious as a fossil fuel, we definitely want to use it as best we possibly can.
And manufacturing, it's a huge energy source. Aluminium, wrought aluminium, primary aluminium, the sort you would find in your drinks cans and things like that. It's 150,000 amps per ton to produce, which is a huge amount of energy. If you could take your recycled aluminium from cans and stuff like that and then use it for primary applications, so reuse it without having any drop in properties, then the UK would meet its Paris Agreement in one go. It would reduce that amount of emissions, because it's so energy intensive. So that's where, again, materials engineers are involved in trying to purify and process this material from a recycled point of view.
Okay, are there any further questions you'd like to ask? Otherwise, please feel free to email us. I have put my email in the chat, but I'll just pop it there again, just in case anyone has any questions that they can't think of right now, but want to contact me at a later date. So my name is Sian, and you can contact me about any admissions questions that you may think of, or how you can apply to any university, and we can guide you with that. Or Dave and Tristan have also given their email addresses. Thank you very much for joining today, and we look forward to meeting you in the future.
Thank you. Bye-bye.
Indeed.
Bye.
Bye, everyone.
Bye.